Hello and greetings, madam. My name is Clarissa Hamijimi and my ID number is 2022499082.
Hello, my name is Nushaira Nadiraminti Erman and my matrix number is 2022624828.
Hi, my name is Nurshafina Eliani binti Salam and my student ID is 20226999 and 504.
My name is Siti Shaira Farhana binti Saturi and my student ID is 2022499902. The topic that we have chosen is nuclear fusion as sustainable energy sources. So first, let's get to know what exactly is nuclear fusion. Nuclear fusion refers specifically to the process by which atomic nuclei come together to form a heavy nucleus, releasing a significant amount of energy. This process holds the potential for being a powerful and sustainable energy source if it can be controlled and harnessed on Earth.
Nuclear fusion is important in modern physics because it fools stars such as the Sun, making it the ultimate energy source as it is the foundation of star energy production. By studying fusion reactions, scientists can gain insights into how stars produce energy and elements, leading to a deeper understanding of stellar evolution and the dynamics of the universe. In one graph, it is giving sustenance towards potential future energy solution here on Earth. Fusion research advances the science of high-energy physics by allowing scientists to investigate extreme temperature, pressures, and plasma dynamics. This research increases our understanding of fundamental physics while also providing practical application in domains such as plasma physics, material science, and particles accelerators.
To obtain comprehensive and credible information on nuclear fusion as a sustainable energy source, a systematic and complex method is required. The methodology that we used to obtain information regarding this topic was entirely based on online databases. For example, Google Scholar and peer-reviewed articles.
When using nuclear fusion as sustainable energy sources, of course there will be challenges faced. Amongst the challenges are dealing with neutron radiation. Neutron radiation is a form of ionizing radiation that presents as free neutrons caused from nuclear fusion. When neutron radiation produced from nuclear fusion, it could and present damage to some constituent materials used on a reactor. It could travel 10 centimeters out into the containment structure, thus the risk of damaging materials is high. Then we have fusion flow. Massive gravitational forces in the Sun provide the ideal condition for nuclear fusion to occur in the star's core, but they are far more difficult to accomplish on Earth. The fusion flow, which consists of various hydrogen isotopes, need to be heated to extremely high temperature, roughly 50 million degrees Celsius, kept stable under high pressure, and dense enough and contained for an extended period of time to permit the nuclei to fuse. Proper solutions have been done by the experts in the nuclear fusion field. One of them are with intense research by professionals through advances in plasma physics. Their first goal was to reach out a break-even condition that occurs when the amount of energy used to heat up plasma is equal to the amount of energy that is produced by the fusion reaction. The plasma physicist is working on a research on fusion energy on reaching a better system of a nuclear reactor. Next, innovation. Reducing neutron radiation by making insulators into a fusion reactor with fusion-relevant electrical field measurements. An experiment done by the National Academy of Engineering revealed that the artifact of electron irradiation condition now doesn't happen under neutron irradiation condition. Their experiment concluded that as long as the electrical insulators aren't affected, the system will be managing well. And then, the material. The using of carbon-carbon composites in plasma physics mechanics have been used for a long time, but it no longer serves a purpose when neutron damage overpowers the system. Hence, a fast-flowing liquid coolant on the first layers of the system is applied to take away the heat. Other than that, they also suggest plasma-facing materials to sparkle surface atom.
The importance of nuclear fusion can be seen in first one is potential of being the next renewable resources. As what has been understood, fusion may provide around 4 times as much energy per kilogram as fission and nearly 4 million times the amount of energy produced by burning coal or oil. The main obstacles in obtaining this objective resides in the power needed to create the fusion process. Ultimately, if its power is generated from renewable sources, then fusion energy is undoubtedly able to provide a long-lasting renewable energy. And the second one is safety for the climate change. It is stated obvious that nuclear fusion are safe as it emits 0 to 9 potential of harmful greenhouse gases and existing non-elastic high activity of nuclear waste. Moreover, nuclear fusion is one of the clean energy alongside other energy non-like wind and solar. Even the nuclear fusion are proved to be safe as the technology and fundamental physics application in the nuclear fusion reactors that makes them far from being dangerous. And the third one is the sustainability for electricity technology going forward to its future. technology developer is in a hurry in finding continuous resources of electricity to ensure the sustainability of future development and vitality. Fusion is chosen to be very potential for creating efficient, long-term source of low-carbon electricity as it is safe and is a promising process in research. It said, nuclear fusion is sure is able to be used to generate electricity, though it is not yet to produce bigger quantities of electricity to be valid of a resource due to the incapability of present technologies. Surely, after being commercialized, fusion will play an important role in the energy market of the future. Now, let's talk about examples related to nuclear fusion. There are two main methods being in observation and conducted regarding of containing the high temperature of plasma needed for fusion reaction on Earth. The examples are the first one, magnetic confinement. This technique uses magnet to trap hot plasma in a ring-shaped chamber called a torus. The magnets keep the plasma away from the edges. The plasma can also generate its own magnetic fields, adding to contain itself. Tokamaks. Machines that can generate the needed condition use this method to trigger fusion reaction. And second one is known as ICF, which is inertial confinement fusion. In simple terms, the inertial confined fusion ICF uses compression, not extreme heat, to initiate fusion by squeezing the fuel really fast. It heats up and creates shock waves that ignites fusion, like in nuclear weapons. In the same way, stars are doing something similar with gravity, collapsing and heating up to generate fusion. To do this, we use powerful lasers or particle accelerator on Earth.
Moving on to the application of nuclear fusion in our daily life. First is, nuclear fusion provides clean and abundant energy. One of the most important applications of nuclear fusion is to generate electricity. Fusion power plants could provide a reliable and obtainable source of energy, reducing dependency on fossil fuels and lessening the effects of climate change. This clean energy source would generate minimum waste and emit no greenhouse gases, making it an environmentally favorable option. Next is, nuclear fusion improves air quality. By replacing fossil fuel power plants with fusion reactors, we could witness a large reduction in air pollution, such as sulfur dioxide, nitrogen oxides, and particulate matter, resulting in cleaner air and healthier living conditions. Third application is desalination of seawater. Fusion energy might power desalination plants, turning seawater to fresh water on a huge scale. This would be especially advantageous in desert regions and communities with limited water supplies, offering a consistent supply of safe drinking water.
For the next part, I will be explaining on recent study on nuclear fusion. Stand as one of the most ambitious projects in the world today, while then being the world's largest fusion experiment, the International Thermonuclear Experimental Reactor, or in short, ITER, is an international nuclear fusion research to engineering megaproject aiming to create energy through a fusion process similar to that of the sun. I know it sounds crazy, but here's how it's worked. The reactor is designed to achieve a fusion power gain of at least 10, and it will produce 500 to 1000 megawatt of fusion power, which is comparable with one of today's electricity generating plants. The application used by ITER to achieve such objective is the law of fusion, by fusing both deuterium and tritium into helium. To do this, they had to construct the world's largest magnetic confinement chamber, or tokamak, which is done in the south of France, to generate net energy, as reported by Euronews.net. This chamber uses the nuclear fusion concept, which is almost identical to the sun. In short, nuclear fusion is the process by which two light atomic nuclei fuse to form a single heavier one, which generates a massive amount of energy. However, in the case of sun, hydrogen atoms at its core are fused by the sheer amount of gravitational pressure. The ITER laboratory states that there are three conditions that must be fulfilled to achieve fusion in laboratory. First, a very high temperature. Second, sufficient plasma particles density to increase the likelihood that collisions do occur. And lastly, sufficient confinement time to hold the plasma, which has a propensity to expand within a defined volume. Therefore, the tokamak is built to fulfill all three conditions. So, how does a tokamak works? The first crucial step in a tokamak is to create a plasma foundation. To do this, both deuterium and tritium gases are injected into the tokamak. These gases are then ignited or heat to a very high temperature, which is around 100 million degrees Celsius, to form a plasma, which is a state of matter where electrons are separated from nuclei, creating a group of charged particles. There are several methods used to heat the plasma and maintaining its temperature. One of them is ohmic heating. With the plasma itself act as a resistor, it heats up as the induced current flows through it. Next one is the neutral beam injection. High-energy neutral atoms are injected into the plasma, thus transferring their energy to the plasma particles through collision. And lastly, radio frequency heating. Electromagnetic waves at specific frequencies are absorbed by the plasma particles, which will increase their energy. Then, the tokamak will use a powerful magnetic field to confine and stabilize the plasma in the chamber. These magnetic fields are created by external coils and an induced current within the plasma. The combination of the two will form a helical magnetic field lines, which keeps the reactor away from the walls, thus preventing it from cooling down while maintaining the necessary condition for the next step. Inside the heated tokamak, Both deuterium and tritium have high kinetic energy, which causes them to collide with each other with enough force to fuse. When fusion occurs, helium nuclei, neutrons, and a significant amount of energy is produced. This energy is mostly carried by the kinetic energy of neutrons and the helium nuclei. The high energy neutrons will escape from the tokamak as they are neutral and do not follow magnetic field lines. Then, they are absorbed by a surrounding blanket of material containing lithium, whereby their kinetic energy is converted into heat. This heat is then used to generate steam, which drive turbines connected to electrical generators, thus producing electricity. To maintain the whole process, a continuous supply of deuterium and tritium is maintained to keep the fusion reaction going. However, there are still challenges in achieving and maintaining the condition for controlled nuclear fusion in a tokamak. These challenges involve the extreme temperature required for plasma formation, maintaining plasma stability and confinement, and lastly, efficiency in ejecting and converting the fusion energy.
There are several promising careers in the nuclear fusion field. Among them are fusion physicists. They work with theoretical and experimental research techniques to comprehend and enhance the mechanics of nuclear fusion. They also take part in designing and conducting experiments, analyzing data, and innovating brand new technologies on challenges of nuclear fusion as energy. Then, fusion engineer. They create, construct, and maintain the fusion reactors with their technical expertise. They also work on power plant systems, including its controls and mechanism. And then we got plasma physicists. Plasma physicists play a big role in improving technology of nuclear fusion and studying the performance of plasmas, which is the hot ionized gases necessary for initiating reactions of fusions. They also conduct research to understand the characteristics of plasma, constructing plasma confinement system, and also the development of fusion reactors. Now, let's move on to the purpose and specific skills needed for career excellence. A fusion engineer requires a person to be highly knowledgeable in nuclear and plasma physics, and also in nuclear reaction, as their scope work will be needing a person to manage the power plant systems. They also need a strong skill in thermal resistance, which means that to have a high knowledge of it, and engineering of heat transfer to manage the increasing of temperature during the process of nuclear fusion. Then fusion physicists. They require a person of expertise in nuclear reactions, plasma physics, and also nuclear physics. Fusion physicists require high understanding of nuclear fusion for making theoretical design, experiment, and analysis to improve technology of nuclear energy process. On to the next one. The plasma physicists require a person to be knowledgeable in nuclear fusion, as it focuses on advancing the technology of nuclear fusion by the behavior of plasmas. It also needs organization and problem-solving skills, as the person will be needing to contribute in the development of fusion reactors.
Among the specific skills needed to apply the career choice are staying up to date with the latest nuclear fusion itself. This can be done by securing an internship or fellowship during your academic training at research institution, national laboratories, or company involved in fusion research such as ITER, General Fusion, and Tokamak Energy. Having the experience in internship or fellowship can also help you to secure a full-time position at those companies to enjoy your future involvement in the next innovation. Next is enhanced technical and research skills. This can be done by obtaining a strong educational foundation in physics, engineering, or any related field. To be more precise, further in advanced degrees such as masters or PhDs focusing on plasma physics, nuclear engineering, or material science is crucial. This achievement will definitely contribute to help establish yourself as an expert in a niche area of fusion research, such as plasma confinement or reactor design. Next is contribute to innovation by doing research and development, as it fosters the ability to contribute to cutting-edge research and technical innovations. To do this, you can undertake independent projects or contribute to innovative R&D initiatives within your company or institution. This will help you to contribute for 2 or at least 2 significant research projects. Lastly, enhance professionals' growth for career advancement. Try to seek mentorship from experienced professionals in the field and regularly discuss your career goals to develop plans with your mentor. In the future, you can also mentor early career researchers and students, which contribute to the development of the next generation of fusion scientists. By obtaining relevant experience and setting targeted goals, you can effectively develop the skills necessary to apply for the targeted career in the nuclear fusion field. So moving on to the last part, which is challenges and strategies for overcoming problems. A career in nuclear fusion presents numerous challenges. However, it can be overcome with the right strategies if it is effectively addressed. So for the first challenge is complexity in understanding the plasma physics, as the plasma behavior is complex and difficult to predict. So how to overcome it? We can overcome it by engaging in lifelong learning through courses, workshops, and seminars to stay updated with the latest advancement in plasma physics, material science, and engineering. The second challenge is resources constraint, as fusion research and development require substantial financial investment, which can be difficult to secure. So we can overcome this by foster partnership between academic institutions, government labs, and private companies to collect both resources and expertise in this field. And as for the last challenges, which is regulatory and safety issues, this is mainly due to ensuring the safety of fusion experiment and addressing public concern about radiation and other risks are paramount. So how do we overcome it? We can overcome it by implying rigorous safety protocols in our experiment done to prioritize safety in reactor design and operation. So to end this, by understanding these challenges and applying effective measurement, professionals in the field of nuclear fusion can control the complexity of their career. This contribute to the advancement of sustainable energy sources.